Hello everyone, welcome to my class. This is still Maths with Victor. Kindly like, follow, and share my Facebook page to all your friends and also subscribe to my YouTube channel. Today, I want us to discuss on something very important and very fundamental to mathematics, the place value systems. This is for pupils in primary school and students in junior secondary schools. The place value system is very important whenever we talk about numbers. So notice something on the board. We have two different numbers. The first one is 6,712, and the next number is 2,167. Two different numbers. But a careful look at these numbers should reveal a similarity or a peculiarity. You will notice that we have 6 here, we have 6 here. We have 7, we have 7, we have 1, we have 1, we have 2, we have 2. That means that these two numbers contain the same digits, yet they are different numbers. So the question is, why are they different? Why are they different? The reason why these numbers are different is that the digits that makes up the numbers are in different positions. 6 is here, 6 is here, different position. 1 is here, 1 is here, different positions. That means that the position of a digit determines the value of the digit. Therefore, the 6 and the 6 here are not the same thing. The 1 and the 1 here are not the same. The 7 and the 7 here are not the same. The 2 and the 2 here are not the same. What determines the value of these digits is where the digits are found, and that is what is called the place value system. The place of a digit determines the value of the digits. Let's talk about numbers. In mathematics, there are only 10 digits. Of course, we know that already, from 0 to 9. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are the only digits we have in mathematics. So beside these digits, any other number is formed by combining these digits. For instance, after 9, the next number is 10. But 10 is not a whole new digit. It's a combination of 1 and 0. So we can get 23 while writing numbers. It's not a new digit. It's a combination of 2 and 3. So while dealing with numbers, there are cases where digits are found in different positions. And these positions determines the value of the digit. And that is what we call the place value system. And that is why this number is different from this number. So let's talk about their place value. All right. So when we talk of 2, the last number here, can I just quickly write this here? 2167. The last number here, 2, is in the value we call the unit. The unit. Unit means 1. So we can multiply 2 with 1, and that still gives you 2. That means this number is 2. 2. That digit is 2. It's the unit. Then this digit is in a value of 10. So it is not 1, but 10. All right? But this is in a value of 100. So this is not 7, but 700. 700. And finally, this is in a value of 1,000. So this is not 6, but 6,000. So we can split these numbers by writing these as 6,006. The rest becomes zeros. And then the next number, 7, the rest becomes 0. So we have 2 zeros. So we have 700. Then the next number, 1, the rest, only one number, becomes 0. Then the final number is 2. So these number and these are the same. So we combine these to form these numbers. So that is why you want to call this number, it is 6,000, because 6 is in thousands, not ordinary 6 as a single digit. 6,700, and because 7 is in 100. So the place value of 6 is 1,000. The place value of 7 is 100. The place value of 1 is in tens. Thousands, hundreds, tens, and then the place value of 2 is in units. So we can see that these numbers can be splitted out in their different place values, and you will have 6,000 710 and 2 is 12. So we can add them together, 0, 176, which is still the same as this, place value systems. So we can look at the values of these numbers. Like I said before, this 2 is not an ordinary 2. It is in thousand because after 2, the next digits, 1, 2, 3, becomes 0, 0, 0. That means 2 is in thousand. And therefore, this 2 represents 2,000. Whereas in this case, the 2 represents ordinary 2. You see why the numbers are different. The next number is 1, but after 1, there are 2 digits, they become 0, 0. This one is in 100. 100. So this one is not representing 1, but representing 100. 100. The next one is 6. But after 6, there is only 1 digit, which becomes 0. 6 and 0. That means this 6 is not representing 6, but tens. In tens. It means 6 times 10, 60, 6 tens. Then the last number is 7, which is there with no other number attached, is the last one, the unit. So for this number, we can combine these things together to produce this number, meaning that 2 is in 1,000, 1 is in 100, 6 is in tens, and 7 is in units. So we can add up together 7, 6, 1, and 2. So you can see from this lesson that these 2 and these 2 are different. For here, the 2 represents 2,000. For here, it represents ordinary 2. For 1, in this case, it represents 100. For here, it represents 10, because it is in 10. It is in 100 here. For 6, in this case, it represents 60. It's in tens. For 6 here, it represents 6,000, because it is in thousands. And for 7, in this case, ordinary 7, for here it represents 700 because it is in 100. And that is why this number is different from this number. So place value is very important because it gives us the value of the digits in any number. So when we talk about place value, in summary, for whole numbers, because I'm dealing with whole numbers, subsequently, we talk about decimal numbers. So for whole numbers, the last digit is the unit. Is the unit. The last one, just like I've shown before, the last one is the unit, and then the next one is the tenths, and the next one is in 100, and is in 1,000. We can proceed further to tens of thousands, hundreds of thousands, thousands of thousands, which is millions, and so on and so forth. Thank you, and God bless you. I will leave you with this. 8, 3, 5, 4. So you tell me the place value of 4, the place value of 5, the place value of 3, and the place value of 8. Thank you. Hi everyone. Good day and welcome to my class Maths with Victor. Kindly like, follow, and share my Facebook page with all your friends, and also subscribe to my YouTube channel so that you can enjoy my contents. Today, we want to talk about expansion of binomial expressions. So we have expand 2x minus 3y raised to power 5. So we'll do this as quickly as possible. By expansion, we are multiplying this term with itself in 5 places because the power is 5. So this means 2x minus 3y multiplied by itself, 2x minus 3y, again 2x minus 3y, again 2x minus 3y, and finally 2x minus 3y. So this term will multiply itself in 5 places. 1, 2, 3, 4, 5. So what we have here now is that we are going to multiply this and this. And then the result will multiply to this. And then the result will multiply to this. And finally, the result will multiply to this. It is quite tedious. It is quite rigorous. But to go through all these processes will take a whole lot of time and energy. But there is a better way to do that, the Pascal triangle. So when we have binomial expansion to a high power, instead of multiplying out repeatedly, we can make use of the Pascal's triangle. So I will clean up this and apply Pascal's triangle to solve this problem. So what is Pascal triangle? Quickly, Pascal's triangle. Pascal's triangle gives us the coefficient of the expansion of binomial expressions. It gives the coefficient of the expansions, and we can pick it up from there. So in Pascal's triangle, we have a triangle of numbers which represent the coefficients of different powers in expansion of binomial expressions. So we have 1. Pascal's triangle, it starts with 1. It always starts with 1 and then it's 1 in all degrees of powers. So we have 1 at the first level. At the second level, we have a triangle, forming a triangle, 1 and ends with 1. You can see the shape of a triangle. Then the next level, we are going to have 3. Here there is 1, here there is 2. We are going to have 3, but it must start with 1 and then end with 1. We need to find the number here. To get the number here, we simply add this and this. 1 plus 1, you have 2. That's the next level. The next level, we have 1. It always starts with 1 and always end with 1. So to get the numbers here and here, we add 1 and 2, you have 3. Add 2 and 1, you have 3. But the next level starts with 1 also. Then 3 plus 1, 4. 3 plus 1, 4. Then 3 plus 3, 6. 3 plus 1, 4. And then ends with 1. Then the next level, 1. 1 plus 4, 5. 4 plus 6, 10. 6 plus 4, 10. 4 plus 1, 5. Ends with 1. And then the next level, 1. 1 plus 5, 6. 5 plus 10, 15. 10 plus 10, 20. 10 plus 5, 15. 5 plus 1, 6. And ends with 1. You can see how we build the Pascal's triangle. These numbers are the coefficients of the expansion depending on the powers. So the first one is that of the exponent of 0, the power of 0. The next one is the power of 1. The next one is the coefficient of the power of 2. The next is the coefficient of the power of 3. The next is the coefficient of the power of 4. And this is the coefficient of the power of 5, power of 6. We can continue building the triangle depending on what we are looking out for. But the problem we have is a power of 5. So we are dealing with the coefficients of the expansion for the power of 5. This is what we need for the power of 5. So the coefficient we need in this expansion is 1, 5, 10, 10, 5, and 1. So we can use this coefficient to solve this problem. So I'm going to clean up that and then solve this using this triangle. As easy as that, as fast as possible. So what we have is 1, 5, 10, 10, 5, and 1. So with these coefficients, we quickly expand. So what we have is you pick out the first coefficient, 1. That's the first coefficient. Then pick the first binomial term, the first term in the binomial expression, which is 2x. 2x. Raise it to the power, the highest power, 5. Then you pick the next expression, which is minus 3y. You raise it to the least power. The least power is 0. So you always start with the highest power for the first term, and then the least power for the second term. So we are done with this coefficient of 1. We move to the next coefficient, plus. Coefficient is 5. Then pick the first term, 2x. We started with power of 5 for 2x, so we start with the highest and go down to the least for the first term. For the second term, we start with the least power and move up to the highest power. So instead of power of 5, the power reduces to 4 for the first term. Then we have minus 3y. The power increased from 0 to 1. We are done with coefficient of 5. Plus, the next coefficient is 10. We pick the first expression, 2x. The power will further reduce from 4 to 3. Then we pick the next expression, the next term, minus 3y, and the power increases from 1 to 2. Plus, the next coefficient is 10. 10, and the first term is 2x. The power reduces from 3 to 2, and the next expression is minus 3y. The power increases from 2 to 3. And then the next coefficient, plus 5. The first term, 2x, where we? From 2 to 1. Power reduced to 1. The next expression, minus 3y, the power increased from 3 to 4. Then finally, the last coefficient, plus 1. The first term is 2x. The power reduces from 1 to 0. The next term is minus 3y. The power increases from 4 to 5. Take note of what we just did. We use the coefficients in the Pascal's triangle and then pick the terms and move the powers from the highest to the least for the first term. And then from the second term, we move the powers from the least to the highest. So for the first term, from top to bottom. From the second term, from bottom to top, in the voice of our president. Well, this is what we have. So we continue from here. So we can now simplify. So we have 1, 2x raised to the power 5. 2 raised to the power 5 is 32. 2 times 2 times 2 times 2 times 2, 32. So we have 32. X raised to the power 5 is x raised to the power 5. Then, in our laws of indices, 0 powers, anything raised to the power 0 is 1. So minus 3y raised to the power 0 is 1. So we're done with this. Plus 5, 2x raised to the power 4. 2 raised to the power 4 is 16. X raised to the power 4 is x raised to the power 4. And then minus 3y raised to the power 1 is minus 3y. And then we have plus 10. 2x raised to the power 3. 2 to the power of 3 is 8. And then s to the power of 3. Then minus 3y to the power of 2. Minus 3 to the power of 2 is 9. And then y squared. That's what we have. Then plus 10. 2x to the power of 2 is 4x squared. And then minus 3y to the power of 3. Minus 3 to the power of 3 is minus 27. And then y to the power of 3. Of course, whenever a negative number is raised to the power of an odd number, the number remains negative. But a negative number raised to the power of an even number, the number changes to positive. So we are there now. So we continue from here. Plus 5, 2x to the power of 1 is 2x. Then minus 3y to the power of 4. 3 raised to the power of 4 is 3 to the power of 4 is 81, I think. Yeah, 81. So we have 81y to the power of 4. Then plus, finally, 1. Any number raised to the power of 0 is 1. And then 3 to the power of 5 is 243. So minus odd power. So minus 243. And then y to the power of 5. So this is where we are now. So we can continue the expansion. So forgive me, I'm going to clean off here. So when I clean off here, I have 1 times 1 is 1, 32, and s raised to the power 5 is 32, s raised to the power 5. We're done with this. Plus 5 times 16. 5 times 16 is minus, is 80. 80 times 3 is 240, I think. Yeah, 240. So plus and minus, minus. So minus 240 x to the power of 4, and then y. Then plus 10 times 8, 80. 80 times 9, 720. 720 s raised to the power 3, y raised to the power 2. And then minus and plus will give me minus. 4 times 10 is 40. 40 times 27 will give me 1080 x to the power of 2, y to the power of 3. Plus 5 times 2 is 10. 10 times 81, 810. 810 x, and then y to the power of 4. And then minus 243 y to the power of 5. All right? So is there any like terms that we can add or subtract? No. So this becomes the answer of this expansion. So we can expand easily using the Pascal's triangle of coefficient of binomial expressions. Thank you. You can always share my video. Enjoy the rest of your